Hello, this time a couple of examples of the use of superposition in analysing linear circuits. I'll work through a couple of examples in this talk. First one. Here we have a circuit with a voltage source here and a current source here. There is a 3K and a 2K resistor, and what we want to know is what is the current flowing here through the 2K resistor. Well, we can analyse this by superposition. Firstly, set the current source to 0. Just consider the effect of the voltage source. We would end up with this circuit here. Well, the only current flowing in this circuit is flowing around in this direction here. There's a total impedance in this circuit of 3K plus 2K, remembering that ideal ammeters have no resistance. So that would be 5K in total. So the current flowing around would be 10 volts divided by 5K, or 2 milliamps. Secondly, we can set the voltage source to 0, and that means replacing the voltage source by a wire, because a 0 voltage source works like a wire. Just considering the effect of the current source here, this is now a current divider. And the current flowing through the 2K resistor would be the input current, 5 milliamps, times the other resistance, 3K, divided by the sum of the resistances, 2 plus 3, or 5K. So that would give 3 milliamps. Combining these two tells us that with the complete circuit, with both sources, the total current through the ammeter should be 5 milliamps. Does it work? Well, we can always check these things on the simulator. Let's have a go. Okay, I've built the circuit. I've set both of the independent sources to 0 for now. First, I'm going to turn on the voltage source to 10 volts. And yes, our prediction that that should produce 2 milliamps of current is correct. I then turn off the voltage source, set it to 0, turn on the current source to 5 milliamps. And yes, our prediction that that should give 3 milliamps is also correct. And if we turn them both on at the same time, yes, the total current through the 2K resistor is 5 milliamps. Good. Let's do another one. This time we're looking at the voltage across the current source as being our output, and note that the current source is now pointing downwards. It's forcing 5 milliamps of current to flow from the top node to the bottom node. What would the voltage across that current source be? Well, first of all, let's turn off the current source and just look at the effect of the voltage source. We would now have this circuit. A 10 volt voltage source here, a 2K resistor. A 0 current source is effectively an infinite resistance, an open circuit. I could just leave it like that. The voltmeter here is measuring the voltage from this point to this point, and there is no current flowing in this circuit because an ideal voltmeter has an infinite resistance, so no current flows through it. No current flows through a 0 current source either, so there's nowhere for any current to flow round. There's no circuit. If there's no current flowing, there is no voltage drop across this 2K resistor. That's just Ohm's law again. The voltage difference across the resistor is the current through the resistor times the value of the resistance. If there's no current flowing, there will be no voltage drop across the resistor. So this point and this point are at the same voltage, which means the voltmeter is just measuring 10 volts, the voltage directly across the voltage source. So my first contribution to my voltage is 10 volts. Next, let's consider just the effect of the current source. We'll turn a current source on. That will force 5 milliamps to flow down here. The voltage source we will set to 0, and a 0 voltage source behaves just like a wire, So I could just draw the circuit like that. Now, the 5 milliamps, none of it can flow through the voltmeter because voltmeters have an infinite resistance. So all of that 5 milliamps will be flowing round the circuit like this through the 2K resistor. If you've got 5 milliamps flowing through a 2K resistor, then the voltage difference across the 2K resistor will just be 5 milliamps times 2K, or 10 volts. But note that current always flows through a resistor from the higher voltage to the lower voltage. So this point here will be 10 volts above this point here. But the voltmeter has its red terminal at the top. The voltmeter is measuring the voltage at this point minus the voltage at this point. But the voltage here is bigger than the voltage here. If I defined the voltage here as being 0, then the voltage here would be minus 10 volts. And that's what the voltmeter would be reading in this case. My second contribution to my voltage is minus 10 volts. Well, that suggests that if I built this circuit and I turned both of these sources on, the voltmeter would read nothing. Because adding up V1 and V2, the contributions from the voltage source and the current source, would give me a total of 0. Does it work? Well, back to the simulator again, and we'll give it a try. Okay, I've built up the circuit here. First of all, we'll turn on the voltage source to its 10 volts, and as expected, yes, the contribution of the voltage source to the voltmeter reading is 10 volts. Turn that one off. Turn on the current source to 5 milliamps. And yes, the contribution of the current source to the voltage here is minus 10 volts. Turn both of them on at the same time, and the result is 0. Yes, works. Great. And this is a much easier way to analyze this circuit than any attempt to apply Kirchhoff's current and voltage laws and solve a whole load of simultaneous equations. Okay, next time we're going to move on and extend this idea to see how it can be applied in some circumstances to components and circuits which are not linear.